So welcome everybody to this Laws of Nature session. I'm very happy to announce our first speaker of this year, Cătălina Curceanu. So I'm happy that you can come here today. She is one of the leading researchers at the Istituto Nazionale di Fisica Nucleare in Italy, in Rome, in Frascati. And she's working particularly in these underground laboratories in Gran Sasso, and I'm happy that she's going to tell us something about the recent developments there today. So please go ahead.
Yeah, okay, so thank you very much for inviting me to give this first lecture of the year. It's really a very big honor. And it's also, I'm very happy to see a lot of friends there. So hello to everybody. I'm going to give you a kind of an overall introduction of the experiments we are doing to test quantum mechanics, in particular the Pauli Exclusion Principle and the collapse signals from the wave function. And it's a mixture of theoretical and experimental presentation. I also wanted to give you a flavor of what experimentalists are doing. So for this reason, you will see that there is a lot of introduction to experimental part in my presentation. Before telling you about our underground experiments, let me tell you something about my host laboratory. Actually, I'm right now in my office. You see here in the Frascati National Laboratories. You see here that's not an alien spaceship, but it's our electron-positron collider. And I show it to you because my activity as well as of my group, it's actually shared between experiments on colliders and experiments underground. My office, it's very here nearby. I don't know if you see my my mouse or my indicator. Do you see it? Okay, so I'm in this office here right now, very close to the accelerator. The accelerator, it's a very unique machine colliding electrons with positrons at low energy. That's a picture from inside. And what we do here is actually to collide electrons with positrons and to study exotic atoms, namely atoms where we replace the electrons with a very different negatively charged particle, which is the kaon, which, if you remember, is done out of quarks, so it contains the strange quark, and it has the very interesting feature that since its mass is 1,000 times bigger than the one of electrons, its energy level comes much closer to the nucleus. And since the kaon is done out of quarks, that's a kind of a way to study the strong interaction at extremely low energies between the strange quark and the normal quarks of a normal nucleus, being it a proton, like in hydrogen, kaonic hydrogen, or something else. So I'm starting with these kaonic atoms because there is a very interesting relation of how we arrived to do experiments in the underground laboratory, because initially we were only working at the accelerators, measuring the X-rays, so the radiation emitted by these exotic atoms when they were created in a highly excited state, then decayed, de-excited through towards fundamental level, emitting X-ray radiation in the domain of keV multi-kilo electron volt energy. So to do these measurements, which are extremely interesting and are also related with the neutron stars equation of states, we still do not know whether neutron stars contain strangeness. There are two theories, one in which strangeness plays a fundamental role. So our measurement contribute to disentangle this, to be part of this disentangling this mystery. But this becomes relevant because to do these very refined X-ray measurements of exotic atoms transitions, we had, of course, to develop X-ray detectors. And along the years, actually more than 20 years, we have developed a series of unique X-ray detectors to do spectroscopy. And at some point, we were wondering, what else can we do with our detectors beyond continuing the fascinating field of exotic atoms research. And that's how we actually arrived to do in 2005. So we celebrate this year 20 years of experiments in the underground laboratory of Gran Sasso, because having us this unique, worldwide, unique detectors measure X-rays, we discovered that we can do a lot of interesting things in quantum foundation measuring X-rays. And that's what I'm going to tell you in what comes next, how we use these detectors for something totally different than standard model research with strangeness on accelerators. So the experiments I'm going to introduce to you in what comes next are actually concerning tests of Pauli Exclusion Principle, and I'll give you a flavor of how and what we are doing in this context, why, what is the theory which might be so crazy as to violate a cornerstone of quantum physics like the spin statistics relation. And then in the second part, I'll go to something different, namely signals coming from the so-called collapse models, which are a particular solution of the measurement problem. And that should be me, according to our electronic engineer, searching for treasures in an underground laboratory. Of course, it goes without saying that while doing this from experimental point of view, we are also investigating from two different points of view the relation between quantum physics and gravity by actually exploring different sides of this possible relation. Okay, so what is the Gran Sasso, where we are doing actually our experiments? The experiments are done in the biggest, not anymore the deepest, but still the biggest underground laboratory in the world, which is posed under the mountain of Gran Sasso. So as such is not really underground, but it is under the mountain at about 150 kilometers from my home institute, which is near Rome. Frascati stays 20 kilometers from Rome. So we can easily access the underground laboratory. And it's under this really beautiful mountain in a gallery which connects two towns. The two towns are L'Aquila and Teramo, and the gallery it's about a bit more than 10 kilometers long. Halfway, there is this lab, which is actually underground in the sense that above the lab, there is about 1.5 kilometers of mountain of rocks, which are shielding all the experiments there. And there are about 30 experiments all looking for beyond standard model physics like dark matter or double beta neutrino-less decay, or as in our case, quantum foundations and so on and so forth. And that's an extremely useful environment because in any other lab, you would be totally blinded by cosmic rays. So we are shielded by about a factor 1 million. The cosmic background residual at that depth, it's only about 1 part per million. And that's extremely useful because allows us to look for possibly extremely rare events, or maybe even not existing one, but setting extremely strong limits. And as I was telling you, there is a gallery about 10 kilometers long, with two galleries going in the two senses. And in one of them, halfway, so about 5 kilometers from one side and 5 from the other, there is the opening of this really, really big lab. Imagine that each one of these 3 big holes, it's as big as a cathedral. And there are a lot of experiments like ours, which do not require huge space, which are posed on the connecting joints of this laboratory. That's the entrance. And the metal door, and while the gallery, you can see it on the left-hand side. It's, of course, only for authorized personnel. So when we enter there, there is a lot of safety procedure to be respected. And that's a part where our experiment is placed. It's in one of these shelters, one of these smaller places where you can install. There are actually about 20 experiments which are installed in these smaller experimental halls, ours included. And the first experiment I'm going to tell you about, it's a search for a possible violation. So that's why somehow it's called impossible atoms, because staying to the present day physics, it should be impossible to have atoms which are violating the Pauli exclusion principle. And I'm going to show you how we do that and which are our results. Of course, it goes without saying we did not uncover signals of Pauli exclusion principle violations. Otherwise, we would have got the Nobel or the Nobel Prize, depending. So we only set limits to the probability that this happened. And we started to do the first timid steps towards a more elaborate theoretical interpretation. And the Pauli principle dates back from the 20s, when Pauli realized, initially as a rule, then becoming the spin statistic theorem, that in an atom cannot be two or more equivalent electrons for which the values of all the quantum numbers are coinciding. So initially it was formulated as a rule, which later on became what we know today as a spin statistic theorem. And this tells us that in nature, there are only two symmetry classes which are being actually realized. The one which belongs to the bosons, where you can have boson condensate, where particles can and sometimes even like to share the same quantum states, and that's also extremely important for technology. Or the other way around, there are particles which cannot stay together, so they can't share the same quantum state in a given system. And this has been brilliantly proven by many authors, including Luders and Sumino, who formulated in 1958 this other proof, which relies on various postulates. Now, why am I showing you these postulates? Because, of course, if you want to break the spin statistics relation, and you might expect to have symmetries going beyond pure symmetry states, symmetry or antisymmetric states, you might expect to violate one of these postulates, which all seem to be perfectly legitimate within the standard model physics. But of course, if you start to crack something here, including like Lorentz group or microcausality, you might expect to start having also, as I'll show you in a minute, violations of the spin statistics relation. And Wally Greenberg, who was one of the initiators of statistics which are not respecting Pauli principle, which are called parastatistics or Q-on algebra, so statistics which are different than the symmetric or antisymmetric, put it even more, let's say, easier to be understood, that the motivations for which you might expect violations of Pauli exclusion principle are connected to other violations which are looked by particle physicists, like the famous CPT violation, Lorentz symmetry violation, or more recently, non-commutative geometry, spacetimes. I'm insisting on this because that's what we have worked out quite recently, but by no means that's the only possibility which might produce violations of spin statistics. I had the big pleasure to talk many times and to meet Wally Greenberg and discuss with him about this and about his Q-on and parastatistics. So if we expect that the standard model which respects Pauli exclusion principle, it's well known and well understood, there is a dark sector here which might embed possible physics which may lead to violations also of spin statistics. So beyond standard model theories, which it's searched for not only for Pauli principle, but basically for a whole series of other issues, including dark matter, dark energy, and many other problems, might bring incidentally also to violations of the spin statistics. So what we are practically doing seems to be very trivial and in some sense is. only in some sense, because as you will see, things become complicated at a closer look. So we use exactly the same method as we used on the accelerator, atomic transitions, only that instead of going for conic hydrogen, we go here for copper, like normal transitions in copper. And I'll tell you in a while why we use copper. But in this context, the transitions in the copper are in the keV range. So exactly in the energy range where the detectors we have developed are perfect, because the kaonic atom signals are exactly in the same energy range. So we found ourselves with these perfect detectors, which is able to measure atomic transition, normal atomic transitions in elements like copper. Now, if one would violate the Pauli exclusion principle, one may expect to have a third electron arriving to the fundamental level. And we have done atomic calculations, so use atomic codes where a third electron was not required to respect the Pauli principle to calculate the energy of this transition. And the energy of Pauli violating X-ray transition in copper to fundamental level, it's slightly different than the energy of the normal, what everybody knows and measure transition in copper, which is 8.04. So if you have a detector good enough to disentangle 8 from 7.7, it means that you can hunt transitions which are a trademark, so they are really a trademark. There is nothing else they are having this energy. So if you measure copper and you see this, a peak at this energy, you're done. That's your signal. So that's our sigla, which is self-explanatory, of course. And there is a more complicated story behind, because in addition to the spin statistics itself, to the Pauli exclusion principle, there is a discussion which it's actually called the Messier-Greenberg super selection rule, which tells you that you'd better look for this type of transition in a system where you bring electrons, so the electrons which are supposed to do this transition are better to be coming from outside. Coming from outside meaning from a current which is circulated in a copper strip. So that's an open system. If you just look at the copper strip without circulating current, you can still do that, but you have to violate an additional rule, which is, and I'm not going to enter in detail, but there is a under classification of possible violations which can be done in a closed system. So you have a shock of matter and you look at it and you expect to see transitions violating the Pauli principle, or you try to stimulate them by bringing a current, meaning electrons from outside, and then these electrons, which you can have quite high currents, 100 of amps, you can get much higher flux, and you are better done with respecting other rules of quantum mechanics. So the method is pretty simple. We have a copper strip, we have a power supply, which means hundreds of amps. Of course, that the current you circulate, it's limited by the target. It's very small. It's like some centimeters with a thickness of 50 microns. So if you have 100 amps inside, it's heated. So you have a lot of heat. So if you don't want to burn out all your setup and all your experiment and underground lab, you also need to cool the target. You have limited capacity to go above 400 amps. So they're experimentally challenging. And you measure the X-rays and you look at the spectra. That's our energy resolution. So that's how we see the signal. So that's the normal transition, while the Pauli violating one is expected to be seen as a shifted peak, clearly visible if there, at least up to some probability. And that's what we do. So we circulate a current, we look at the transitions, and we see whether there is something here. Of course, that said like this seems to be easy and trivial, but experimental-wise, if you really want to make an extremely refined experiment, becomes really complicated. Becomes complicated in many ways. First, because as I told you, the target, which it's here, you don't see, but we have a 50 microns target, which need to be cooled. So we have a water flowing circuit which cools the system. Then our X-ray detectors, which are silicon detectors, but used for spectroscopy, so not for positions, need to be cooled at minus 100 degrees centigrade. So it's very, very cold. So it's a kind of interplay with various temperature, with vacuum. And so target in principle is very hot, but the detector, which stays very nearby, needs to be very cold. So it's experimentally, it's challenging. But so, yeah, that's how we do the experiment. Moreover, as I told you, it's true, we are in the underground lab. And it's true that we get rid of the cosmic background rays. But there is still a lot of background radiation which comes from the mountain itself. So you might know that in the rocks and underground, there is uranium and thorium. So there is a lot of radiation coming from the environment. And that means that we further need to shield. So all our apparatus, it's surrounded by layers of lead and copper to try to cut as much as possible. That's part of us. What you see here, it's not even the experiment, but it's the lead, ultra pure lead box, which surrounds the apparatus, which I showed you here previously. So experimentally, it's extremely challenging if you are running for extremely, extremely sensitive experiment. And a first result actually coming from 5 years ago, which we set a probability, a limit on the probability that the Pauli exclusion principle is violated for electrons by respecting, in addition, this super selection rule, which we got, you see, it's extremely small, it's 10 to minus 42. And we extracted this, so you can see that the spectra are still, so it's not that it's nothing here. We still have a lot of counts. Now, part of these counts, whatever it's from here, so below 7 keV, it's put by us there. We have an iron source for calibration purpose. So this is introduced by us to calibrate the detector. But whatever it's above here, like copper lines and residual background, it's due to the fact that we were not good enough to cut the environmental background well enough. So we still have a lot of background. And we run a period with a very high current, hundreds of amps, and a similar period, same number of days, without current, which we used for background purpose. So that's the probability, 10 to minus 42, we got 5 years ago. And so it took us a lot of time to gain a factor of 10. So you see, from 2020 to 2025, we refined our experiment and succeeded to get a factor 10 in the probability. Actually, more than 10, it's more like a factor of 20 or so, because we got for 45, 10 to minus 43 to 2. So we get a factor 20 in the probability. That's an article which was out in December, so less than 1 month ago, in Scientific Reports, with this probability, where we are also discussing the importance of this measurement for the QON parastatistic model put forward by Wally Greenberg. And that's a very, very small number, as you see. So beyond the parastatistics, which is more algebra than physics interpretation, we were actually doing the first steps towards understanding how our limits are translated into limits on quantum gravity models. And for this, we have worked a lot with, in particular, with Marciano, with Antonino Marciano and with Andrea Dazzi, who were proposing this non-commutativity of space-time in the form of K Poincare or theta Poincare quantum gravity models, which are bringing to the violation of Pauli exclusion principle but the probability of violation depends. It's not a universal number like in QAnon models. Here it's a universal and forever number standing independently of energy as it is. Here instead, the probability of violating the Pauli exclusion principle depends on an energy scale. So much so that it's maximal towards the Planck scale or towards the energy scale where space-time non-commutativity emerges, while if you go to lower energies, like our daily normal nuclear physics energy or even high energy physics energies, it scales with the energy and it's a leftover of the big energy scale where the non-commutativity is emerging. If you are interested to look into this, we published 2 articles in Physics Review Letters and Physics Review D in 3 years ago, where we actually excluded beyond the Planck scale the theta Poincare quantum gravity model, and we approached like nearly 10% of the Planck scale the other model. So it's a very effective way to exclude quantum gravity models. This is what I told you before, that there are various models which are scaling with the energy and the emerging scale of the energy, while the power gives you the model. For the power 1, it's the kappa Poincare, then we have the theta Poincare for the k equals 3. We get this Kowalski, Glickman, and Smolin triple special relativity, and so on and so forth. So we are very happy about this because we succeeded to find a handle to start to look, to have a glimpse into quantum gravity models which are connected with non-commutativity space-time, which in turn are predicting very small violations of Pauli exclusion principle. Right now, we are also investigating, we started to investigate, we didn't yet publish, but we are going to, a connection with the minimal length and with the holography by following a similar trajectory. And of course, talking to you, I also am addressing here towards possible new ideas with interpretations of any theory which might bring to spin statistics violation through a path which can go out of any one of the postulates which I showed you before by Zumino, showing that spin statistics, it's connected, it's grounded into 5 postulates I showed you before. What we are doing from experimental point of view right now, we are preparing a new version, which is VIP3, violation of Pauli, the 3rd version, where we are using new detectors, which are not infinitely, but much better than the previous ones because they are thicker, so they are much more efficient in energy for higher energies. And I also want to remind Lev Okun, who was working a lot on the decay of the electrons, actually. So he predicted some interplay between the stability of matter and Pauli exclusion principle. And he was actually insisting very much, I also had the pleasure to meet him in person, on the importance to test the Pauli exclusion principle over the entire periodic table. And that's what we are planning to do. So our detectors, you see, are having a higher quantum efficiency over a broader energy range with respect to those which we are using now, which means that we will be able to go beyond copper to chemical elements like silver, stanium, or palladium. And this experiment is right now in preparation, hoping to achieve similar limits like 10 to minus 40 something and beyond, and try to look into how this depends on the energy scale, because energy of the transitions are different in these elements. So you gain some factor because the energy is not 8 keV anymore, but goes towards 30. So you get quite a boost if you look into the power of energies. So what I showed you here, it's the connection between quantum gravity and Pauli. We succeeded to to establish a direct connection between quantum gravity and Pauli Exclusion Principle violation, but that's by no means the only connection we can establish. So there is a broad sector here, and I'm sure that there might be even something we even didn't think about. So that's one of the things I'd like to convey in this seminar, that I'd like to stay in touch with those of you who are interested to explore further on possible connections. Some years ago, actually in 2018, we also published a paper in Saint Courier, which is not a scientific paper, but it's more a philosophical implemented paper, like why on earth would you look to the violations of Pauli Exclusion Principle, and as such, this article still remains valid. So the grounding in the even philosophical part, it's still fully explained in this article from some years ago. I'm going now to the second part of my presentation, namely the one which relates the detectors of radiation on which we are experts, to a search of another thing like like the collapse models. And I'd like to start with a kind of a joke. So that's the town where I was born. It's a town which is called Brasov. There is a lot of snow. Actually, 2 days ago, temperature nearly reached -20. And this town actually finds itself near this beautiful castle, which is the Bran Castle in Transylvania. And if I tell you this, you might already imagine Bran Castle, Dracula Castle. You may imagine that this is connected with, of course, the Vlad Tzepes and all that zombies, and yeah. And how is this connected? Yeah, the joke is that what else could I do than work on a Schrödinger cat? So coming me from Transylvania, by the way, I share also the same birth date with Vlad, the Count Vlad, which by the way, it's 2nd of November. So it's everything it's kind of made of. So I could, I was drawn naturally to study the Schrödinger cat paradox of this cat, which is alive and dead in the same time. Okay, now going beyond the joke, the second part of the presentation goes with showing you our other part of activity, which it's related with the collapse model, which investigate, as many of you are doing, and in many facets of this fascinating measurement problem in quantum mechanics, we are exploring one of the possible solutions of this problem for those who believe that this is a problem, which is not always the case. But yeah, I know many of you are working on different type of interpretations or even solutions, like de Broglie-Bohm, which quite recently, and we are also exploring the possibility to do some experimental investigations in this sector. The many world interpretations, which are very, very nice, but unfortunately, at least from many world for now, it's not much to do from experimental point of view. And last but not least, so that's a kind of many world of which I told you, for the moment, from experimental point of view, it's hard to imagine something you may do, but if one day this will come up, we would be totally keen to discuss how we can do an experiment. While the collapse, so the genuine collapse models, those which were developed also with support of Lois Dioggi, whom I saw there, are actually a genuine solution of the measurement problem, because they are modifying what we know as a Schrödinger equation with some additional terms, which are not linear anymore. So the whole issue of the root of the measurement problem stays in the linear character of the Schrödinger equation. So what you put in, you propagate basically forever, or at least until you don't break down the equation with the with the decoherence. So you have here additional terms, which are what are called the collapse models. Now, don't take my presentations from theoretical point of view as something extremely solid, because I'm going to insist more on the experimental part. What I'm telling you from the theoretical part has been already discussed Actually, in quite a few of these lectures, I've seen quite few of them where we directly or indirectly this model in different forms, including the decoherence, came over and over. This is a slide which actually says something more. So the collapse model, at least in their genuine original forms, are a modification of quantum mechanics. And for some of the proponents, they are hinging towards a new theory, which we don't know yet what is that theory, which is beyond the quantum mechanics, which I know for many it's a kind of a blasphemic statement, but stay with me and at least, yeah, let's go to see what experimentalists are doing. And as such, if you might assume that there is something more which breaks down the superposition of states, it's very easy to find the reason, at least possible reason for this to happen, which has to do with kind of a gravity. So that's a very direct way to put it. Can gravity in some way cause the collapse? And models have been proposed along the years. Some of the models do not care of what is the reason of the collapse. They are very generic. Are models which originally were proposed by Ghirardi, Rimini, and Weber, more recently are developed by Angelo Bassi and many others. And other models in which you are actually you are assuming that the collapse is related with gravity. And these are again here two different ways to put it. Roger Penrose and Lois Dioggi have arrived to the same more or less equation, but from two different points of view. Penrose started with general relativity, while Lois with the Schrödinger-Newton equation. But strange enough, or let's say interesting enough, they came up to the same from experimental point of view with the same type of equations. And being these only models, so not fundamental theories, they have parameters. Parameters which in one case are the frequency of the collapse, so how often the linearity of the Schrödinger equation breaks down for the single particle, what's the frequency of the collapse, assuming some length of the correlation length in the generic CSL models, or in the Dioggi-Penrose model, there is a characteristic length parameter where which characterize these models. And what it's our key of accessing these models. So there are many possibilities to do experiments. Of course, a very direct one would be to do interference and to look for disappearance of interference where you expect still to be under control, unexpected disappearance of interference for bigger and bigger systems. And that's something which is presently being done in many groups, including Southampton, Ulbricht, including the group of Arndt, Aspelmeyer. So there are many, cantilever. So there are many groups which are trying to access directly the disappearance of quantum features, quantum superpositions. But the limits which you can pose there are not very strong. We are following a totally different road, which is connected with emission of a spontaneous radiation. So the kind of a interaction with this external noise makes so that all the particles are kind of shaken constantly. And this kind of being shaken, let me show, are actually inducing particles, free or not free, even those electrons and protons embedded in normal matter, to emit a spontaneous radiation. This spontaneous radiation has some features. So has a spectrum, which is a continuum spectrum, which goes like 1 over energy in both models, gravity-related or general models, goes like 1 over energy. So it's not like Pauli principle, where you have a sharp peak at a sharp energy. So it's there, you know it. And here instead, it's like a continuum in energy. I have to make a statement here. Roger Penrose, but also Loyosh himself, are not very happy with this spontaneous radiation. And Roger, I know he's looking for a model where radiation is not yet there. So I don't know if he found it yet, but it would be very interesting to see dynamics which respects the physics we know, where you don't have the radiation. So for the moment, I'm going into the statement that there is staying to known physics of radiation, spontaneous radiation, which has a continuum spectrum like 1/E in the simplest cases. And that's what we were looking for. I show you a first article which we published in Nature Physics in 2021, which was creating quite a wave of comments and of interest, where we mostly focused on gravity-related wave function collapse, because I'll show you in a minute how, because of what. For this type of measurements, we didn't use silicon detectors, because silicon detectors are limited in energy around some 10, 20 keV. We used a much broader energy detectors, ultra pure germanium detectors, again, at Gran Sasso. Again, you don't see them because they are embedded in lead to protect from environmental radiation. And that's a kind of a scheme. So there are ultra pure germanium surrounded again by ultra pure copper and lead to shield them for radiation coming from outside. And we measured a spectrum. You see, you never get zero. So whatever you do, you don't get zero, even if you expect zero, but that's still residual background. So we analyzed what we still measured. This is gamma rays, it's not X-rays anymore. And that's what we have published in our paper with this measurement, which actually excluded at least the simplest version of Dioggi-Penrose model, which was expecting to have a cutoff parameter here, but our limit was beyond that. So the conclusion was that if radiation is there, the simplest version of the model, it's excluded. I insist on the simplest because that does not mean that we excluded the collapse model altogether. Only the simplest version, which is nice, because if you exclude the simplest, you can look into the real physics of what it is behind. And we also set limits, very strong limits on the CSL models. This is a second paper published again in that period. Also with Angelo Bassi and with Sandro Donadi. He was the first author because they contributed quite a lot in this research. Later on, we actually last year, about 1 year ago, we looked into the spectrum, which initially was 1/E, 1 energy. But if you look at the atomic structure, some more complicated features due to the electronic shells are coming into being into the spontaneous radiation. But you shouldn't worry about this. The only thing which comes interesting is that we convinced the biggest experiment in Gran Sasso, the xenon experiment, which is the biggest and in many senses the fanciest experiment in Gran Sasso, to work together. And we are now publishing a paper, you can find it already on the archive, where we set extremely strong limits with their data. So they also measure X-rays, and we analyzed together their data, and kind of we excluded the proposed limits for this model. Still a wide space here, it's still available, but in the near future, we are going to eventually close it, which again doesn't mean that collapse models are excluded, means that white noise collapse models are excluded, which makes place for interesting solutions where you look for dissipative models, memory models, cutoff models. That's again one of our papers where we are pioneering this dissipative spontaneous collapse, with Lajos having played a fundamental role in this. So that's a very fun paper, which again we published 1 month ago in Physical Review Research, about the impact of the collapse model. So there is uncertainty, not only in space, but also in time. So we investigated how uncertain are the clocks. And we arrived, of course, what to be expected, that from our limits, the clocks are expected to be not precise, so uncertainty, the fuzziness of time over the whole duration of the lifetime of the universe, which is here, it's expected to be 10 to minus 25 seconds. So in no way important for atomic clocks, but that was a lot of fun to see that time itself, you know, time in quantum mechanics, it's still a big mystery. But there is a fuzziness. If collapse model have anything to do with reality, you might expect that time can't be defined better than that. Right now, we are preparing new experiments, of course, and we are developing not only new detectors, shielded better, with fancier electronics, with, again, it's a lot of fun working in Gran Sasso. But we also are exploring how to use machine learning and artificial intelligence to analyze the data. That's a technical paper we are publishing right now in GINST, where we show that the algorithms of machine learning to clean the data, that's the only thing we explored up to now. Now we plan to use it for physics as well, are extremely rewarding. For those who are interested, I'm going to skip this part, but having us these beautiful detectors of radiation, we also have made the first step towards measuring light emitted by germinating seeds. So very interestingly, lentils, when they are germinating, are emitting light. And if you are interested in this, look at this, our paper published 4 years ago. Now we are publishing another one, where we studied the characteristic of this radiation, and we checked that it's not emitted with the Poissonian statistics, but it has some complex feature within. So that's something beyond what I'm telling you now, but if somebody's interested, we can also discuss. Okay, so that's I arrived towards the conclusion. So of course we are studying the quantum physics, and we do this studying it underground. We study the Schrödinger cat paradox, with many people being puzzled of what we are doing, and Pauli Exclusion Principle. And yeah, what I can say is that, of course, this could be the discovery of the century, but of course, depending on what we find here. So looking ahead and looking for collaborations, there are, of course, open questions. Can we refine our models, both for the collapse-induced radiation and also for Pauli exclusion principle related to quantum gravity or other theories of models? From our point of view as experimentalists, on one side, we are improving it's very hard, but we are doing it, improving experimental capacity and look for synergies with other labs, not only underground. Actually, we now initiated a European Marie Curie, we won a Marie Curie grant for underground laboratories. So we start now to work with Canada lab, with Snow Lab in Canada, and with the Australian lab near Melbourne, trying to set some quantum foundation studies there as well. And of course, one of the reasons for which I'm talking to you now is we look for collaborations opportunities, both in theory as well as an experiment, to get this interface between foundations and quantum and gravity. And I want also to tell you that there is actually cost action. Probably some of you are members of this cost action. Started 1 year ago. It's called Bridge Quantum Gravity. If you wish to apply, please apply. It's having various working groups, some on theories, some on experiment, which has the goal to bridge high and low energy experiments and theories in search of quantum gravity. And we are planning to organize a workshop at Gran Sasso in this period, 17 to 20 December. And if you are a member of the cost action, one can get support for this. So with this, I thank you very much, and I'm here happy to answer possible questions or suggestions. Thank you very much.
Thank you very much, Cătălina, for this very nice talk.
I don't know if I should stop sharing or keep the talk. What do you suggest?
Yeah, depends. Maybe if you want to see all the people, it's better to stop. But if somebody has a question, then, well, then you can start again to share.
Okay.
Okay, there's a first question already by Daniel Sudarsky. So, Daniel, please. You raised your hand, yeah.
Yeah.
Now we
Thank
see.
you, Cătălina, for a very interesting talk, as usual. I wanted to ask you, and actually the rest of the audience, perhaps people have thought about this, but I have been concerned with the, putting together collapse theories and gravitation. And one issue one faces in dealing with that, which makes the problem more complex, is the fact that collapse generically will be associated with non-conservation of the energy momentum tensor, which makes the whole theory inconsistent in a sense. Something similar I expect to happen in electrodynamics. Quantum electrodynamics requires conservation of the charge for the theory to be self-consistent, the conservation of the current, actually, for the theory to be self-consistent, not just the overall charge, but the current. And I expect generic collapse theories to be in conflict with that, right? If I have a charge that is in a superposition of being in two places and suddenly I force it to be in one place, I expect the expectation value of the charge to jump in a drastic way. So the issue is, how do we confidently compute emission rates using a theory, applying it to a situation in which the foundations of the theory are questionable?
Well, calculating it is very easy. Once you give up to the conservation of energy, of course. So,
right, but how do we trust? What is this self-consistent theory that we trust on in making that calculation?
Well, the problem is that in this case, as far as I understood it, Lajos is there to comment, it's that you don't have a self-consistent theory anymore. You're
then how
open
do
up.
we trust
It's a model which would actually show the way towards something which should become the self-consistent theory one day. So on one side, you're now having like it, as I see it, it's like when the Newton theory was replaced by the Einstein general relativity theory, you had features, of course it's different, but you had features which you cannot explain from the point of view of the Newton theory. They only make sense from the other one. So in how I look at it, it's that you are expecting to get a new theory one day where everything will make a different sense. So this is a kind of an approximate model where you are searching for radiation to hint towards this new theory.
Basically, we compute using the theory that we know and that we believe is not right, to put bounds on a theory that we think may be right.
Yes.
Okay. I invite anybody else to share with me, because I'm very
I think that Lajos, who is one of the authors of the theory, if he wishes, he may. But yeah, well.
Lajos, you wish to comment on this? No, I think he doesn't want to.
I could give a very
we don't hear you, Lajos. You're muted.
I remember that at the dawn of quantum mechanics, Werner Heisenberg could imagine a very, very tiny violation of the energy conservation rule. So it happened already that some fuzziness was on the table, and if space-time has any kind of fuzziness, it may mean that energy conservation, energy momentum conservation is not the ultimate and sharp rule.
Right. No, I don't have a problem with that. My problem is what theory we use to predict effects of those modifications.
It's a theory which contains some fuzziness, some stochasticity at a very low level, at such a low level that no one was able to detect it.
Yes.
This is our task now, that these crazy modifications, crazy predictions toward tiny violations of sharp theorems and sharp conservation rules. So, I mean, these crazy tiny violations are not yet at the threshold of detectability. So this is the open door, a challenge for experiments.
Yeah.
But it's also a challenge for the theoreticians.
Yes, because we have to create smart predictions which are not too crazy, which can be hidden for the coarse-grained detectors in everyday labs, which might pop up when we, on purpose, would sharpen our detectors. So it is a challenge for the theory. It is not by chance that there are not dozens of competitive theories of spontaneous collapse, but only a few ones.
Exactly.
Okay, thanks. So
thank you, lawyers.
Thank you.
Yeah, I would
Thank
like
you
to go on. Thanks to the next question. So, Michael Steiner, you have a question.
Yeah, can you hear me?
Yes.
Okay. No, this isn't a question, it's just a comment on the previous question on energy conservation. And my comment is that I think that Daniel Starsky is correct, that the theory is wrong. All these theories are wrong. The theories that you're looking at with these theories that all predict energy non-conservation. And really what's not been developed is a theory that has energy conservation. In fact, we've been working on a theory for like 30 years. It's unpublished. But we have a threshold that we found, and it's completely energy conserving. And one of the predictions it gives, and none of this is yet published, but it will be. But one of the predictions is simply positron, electron annihilation. Well, there's two predictions. Positron, electron annihilation is a measurement. And the other one is that just a neutron or, nuclear reactions
Sorry, what's
are
the
measured.
prediction about the electron annihilation?
That's a measurement. In other words, it doesn't occur in superposition. You either get annihilation or you don't. And the other prediction is that a neutron, nuclear reactions like emission of a proton is also a measurement. So you don't get that in a superposition. And they're right at our threshold. So we have a threshold for measurement. And below the threshold, you're unitary, and above it, you can be measurement. And these two processes are right exactly at the threshold. And they're all energy conserving on every trial. So you also have to conserve energy and momentum on not just on average, but on every trial. So I would add that to the issue. And there's a major error made in our view, I don't know, it's really they overlooked an error. The DOC, Penrose, and all these theories make an error, and this error causes everything to be non-conserving. And so that's the major issue that Sudarsky raised. that you need to really think about. How do you make an energy conserving, momentum conserving on every trowel?
Okay.
And that ends up leading you to a threshold.
Yep. Let me just clarify.
Are you so sorry? Are you planning to publish this?
Yeah.
Okay.
But it's taking time because it's been over 30 years we've been doing it.
Okay.
And so, but this next couple of years, we'll be publishing it in the next few years.
Okay.
There's three parts to it, but we will be publishing it.
Okay, cool.
Okay, so we are looking forward to that.
Sorry, just a very brief comment. I just want to clarify. I think it's what Michael said is very interesting. I look forward to seeing this theory. It was an interesting theory, but I'm not claiming that any theory that has no conservation is inconsistent. What I'm saying is that we need to refine the theories to allow, if the theory is going to have energy or some other type of non-conservation, we have to refine the theories to address this issue. So I'm not making the much stronger claim that Michael is making, that that such theories should be viewed as inconsistent. So my claim is weaker.
Okay.
Okay. Great. Next question is by Dirk.
Yeah, the first part is also just a comment to this discussion. I mean, you can view these experiments, of course, also without any theory, just checking on things that we can measure. And these experiments, and I think, although I'm not really a collops guy, let's say, but the development in this part of theory has driven experiments to utmost precision, from which everything will, in the end, take advantage. Yeah, no matter which theory is right or wrong.
Yeah.
So I think it's good on the one hand side to do commitments in terms of, oh, I want my theory to be this and I want it to be that, and so on and so forth, and see how far we go. But on the other hand side, it's also good to say from the experimenter side, let's have a look, yeah, what these things do. And maybe in the end, I mean, it could even be, as I said, I'm not a really, I would like my world also to be energy conserved and momentum conserved and so on, but that's not up to us. I mean, the experiment will decide, and any theory could, for example, that allows for prediction of violations can be tested now. Yeah. So, but that's just a little comment to see that there are two sides, at least in my opinion. But my question would go in the direction, maybe a little bit in the same thing, as the Pauli Exclusion Principle. What was the history, or how did it come up in? I mean, it's such a strong principle somehow. If you look at how quantum mechanics is taught nowadays and so on and so forth, what was the history where people said, "Oh, that's a nice source. Maybe we can find a violation there"? Was it because in quantum field theory one discussed a lot of mechanisms of symmetry breakings to see new effects, or what was the source? Where came the interest in particular experiments about Pauli Exclusion Principle?
So it came from Pauli himself. So in his Nobel lecture, Pauli was actually stating that we have that he feels uneasy that we don't have an explanation of why such a rule of nature should be there, why mixed symmetry should not be there. So that was this is what he said in his Nobel lecture. Later on, Feynman, in his physics lecture, was adding something very similar. So was kind of saying that he's bothered by the fact that nature does not realize symmetries that this or that. So, but that's kind of very generic philosophical statements even. Later on, when people started to look for violations, initially was, motivations can be from many points of view, but initially was due to the parastatistics. So Wally Greenberg came up in the 60s. Well, initially the parastatistics were invented when the color was not there for quarks to explain the omega minus minus. So when it looked so bizarre that we have a particle which was omega minus minus with three strange quarks in the same quantum states when color was not yet there. So he had to invent some statistics which was kind of violating the Pauli principle, so he invented the parastatistics. But then the color came into being, and parastatistics were not necessary anymore, at least not in quantum chromodynamics. But the parastatistics remained there, and they were used actually in the history when the beta radiation, the beta minus radiation from cosmic rays was discovered, and was used the other way around, in the sense that the Pauli principle was used to prove that the beta minus, it's identical to electrons. Even if the word identical was, somebody told me, and I think I agree with him, that I should never use the word identical, but not distinguishable. And I tend to agree. So the history, it's very long and very fascinating. And when this happened, people started to turn it around. So put this all together along the years. So statement of Pauli, statement of Feynman, the direct use of Pauli principle to prove beta, its electrons, they flipped it around and turned back to parastatistics. Meanwhile, Wally Greenberg developed a theorem which shows that CPT is related to its spin statistic and with Lorentz symmetry. They are embedded one in the other one. So if you violate one, you should violate another one. So if you violate CPT, you expect to have violation of spin statistics. So that's a theorem. So that was between algebra and CPT and Lorentz symmetry. We came later on, only 5 years ago, as you saw. These are pioneering articles with relation with quantum gravity. So that's very recent. So making an additional step to all this complicated tower. I want to comment on your first comment, though, because when you don't conserve the energy in the standard model, that's not so weird, because Daniel himself, I know why he made his additional comment, because Daniel himself was exploring the idea that you may still conserve the energy, but you may find it as a dark energy or something else, something motivating the evolution of the universe. So you might not conserve it from the sector, from a bigger sector, which you are still looking for.
Yeah, thank you very much, Cătălina.
I have also a question. So I wanted to ask you if you know, is there any experimental way to, let's say, distinguish? I mean, all people are speaking about quantum gravity models and all kinds of quantum gravity models nowadays, but I mean, there exist also other models where you have a classical gravity and just matter is taken to be quantum. So kind of semi-classical models. Do you know if there's any experimental test to distinguish this from pure quantum gravity? I mean,
well, I don't remember. Paula, you are in the bridge quantum gravity cost action? I don't remember.
No, I wasn't.
You should, because we spent, I don't know how many days discussing this.
Okay, see, I missed that then.
Because there are many ideas which might show that quantum, the relation between gravity, indirectly, that gravity is quantum or not. And these are famous. I'm not going to repeat them here, these proposals, which are not very clear for everybody that they are doing what they are claiming, but that's another story. I don't want to enter into that. But the only thing which I can advise, if this is for interest for you, just apply to this cost action, because there is a lot also of interesting seminars, online seminars going on, part of them fully dedicated to this.
Okay, I see. Yeah, then I will do that.
Yes, please.
Okay, so if there's not any other question, I think.
Can I maybe?
Yeah, there, Wojciech, you have.
Hi.
Go ahead.
Hello, Cătălina. Thanks for
Hello.
a beautiful talk. I was particularly interested in this part about models on non-commutative space-time, since that was a very hot topic when I was young. I was not really involved, but that was like the only right approach. What's the take-home message of these experiments? Are some of these models excluded? Do you think this idea can be saved and is worth pursuing, this theoretical idea of quantum field theory on non-commutative space-time, or the bounds you have are so sharp that probably, there is nothing interesting in this corner?
No, I think quite the opposite. It's very interesting, and what we are actually starting to show is that, as expected, actually it's not so weird, that low energy experiments, but with extreme precision, can have a world where accelerators cannot. So you can't do at LHC what you can do in extreme precision experiments. Whether non-commutative models, I think that the fun part starts only now, because if you, as a theoretician, you believe and you know that there is a way to test them somehow. And we excluded only, let's say, such a small amount of a huge empire of models that it only makes it more fun.
I see. So, okay, but I think there is also a huge pile of papers about this model, so probably you would be busy for a long time excluding all of them.
Yeah, that goes without saying for any sort of beyond standard model theory.
Yes.
Unless we hit something. So the hope is that you hit something. Always, of course, the hope is that, but one should also be realistic. So, but my hope, my hidden hope, is that at some point we will measure something that we don't succeed to get rid of.
I see, yes. I keep fingers crossed that there will be surprises. Thanks.
Thank you.
Okay, thanks. So there's another question by Dirk, or comment.
Yeah,
I don't know.
If I may, no, this time it's not a comment, no worries. No, but a similar question. You said something, or at least I picked it up quickly, that you said something about these white noise models in collapse, and it sounded very promising or very optimistic that somehow the bounds can be closed in the near future. Could you just elaborate a little bit on how close are we to this day? And
well, I think it's a matter of up to 10 years. So up to meaning it might be also 2 or 3, but closing with the spontaneous radiation, caveat, with the spontaneous radiation, we will close the gap of white noise in up to a decade.
Okay, and then the non-white noise models we should conceive probably as some effective model of some underlying theory that somehow engraves the signature into the noise.
Yes. You need to be a bit more creative because white noise are not realistic anyway. So they integrate to infinity. So you need to have some physics motivation behind them to make them more physics related than kind of, yeah.
And are there some ideas or some fields?
Oh yes, Angelo Bassi already published some with Steve Adler. They already published some first models. Well, they are not very sophisticated. They have a cutoff. So they simply have a sharp cutoff, sharp or less sharp. But yeah, it's the question is
about those models that they also use non-white noise, and that I more or less knew. Just the idea, I mean, or what are the ideas that influence the color of the noise? I mean, is there some, or there are some thoughts available, like what could be the source of the colorness?
Yeah, we are discussing this. Okay. We are discussing this. Also with Daniel, we were kind of discussing that in a context of very early universe.
Okay. Yeah, looking forward to that.
Yeah. We were also with Daniel.
Okay, thanks. So there's another question by Marilu Ciofalo.
Yes. Ciao, Catalina.
Ciao.
Thank you so much for this beautiful talk.
And thanks to Paavo Pilkkanen, because he informed me, otherwise I would have not known about this wonderful occasion. So, quick question. Well, I don't know whether how quick it is, but do you think that this kind of experimental theoretical joint effort could also cross the problem of quantum time, and the problem of quantum time be useful? Also, for example, say, proposing experiments that can be made with similar concepts as those some of those that you have illustrated, or maybe more like in the direction of what Marcus Aspelmayer, etc., are doing?
Actually, I do think so. And this paper I showed you with the clock, with the fuzziness of the clocks, it's our first approach towards looking into the relationship between effects on time coming from the theory. So it was motivated exactly from this point of view. So yes, I do think so, but I also think that
sorry, Catalina, which of the papers you showed? Because I entered a few minutes later.
Oh, it was, sorry, I'm going to re-show it. It's, where I am, my God. This paper.
Oh, yeah, okay, yeah. Mm-hmm.
Yeah, this is our first approach towards the effect on timing. And it's by no means the only one, because of course that non-commutativity, so that's from collapse models. Non-commutativity has some other effects in the locality, in the microcausality violations. And that's a total different sector, which we are thinking to explore.
Okay, wonderful. Maybe we can have a chance to talk.
Yes, we have to. We have to.
Thank you so much.
Thank you.
Okay, great.
And of course to the organizers as well.
Oh. Welcome. Thanks. There's another question by Daniel Sudan.
No, it's not a question, it's a request. Catalina, would you mind sharing your slides? So
absolutely not.
For those that we didn't take notes.
Absolutely not. Absolutely not.
Yeah, that would be great.
Should we just ask me on the website, or should we share it? Do you share it privately? Just
I can send it to you. You can share it.
Great.
I have no issues.
If you have no issues,
fantastic.
you can also put it on the website.
I'll send to Fabian.
Okay.
Perfect.
Okay. So any other question, comment, request, or something of that kind? So if not, yeah, I'm happy that we have you here, Catalina. It was very nice to meet all of you.
Just a message, Julian, we will keep in touch.
Oh yeah, Julian was here, or is here still?
Yeah.
I think he just left. Yeah.
We didn't hear you, Julian, but
Julian Barbour.
Yeah.
He's there.
Hi, anyway. Okay. So thanks to everybody for coming, and see you soon in our next seminar.